The final podcast of session 1 will cover hybridization and sigma and pi bonds. I always tell my students that the more Greek letters you can put on your paper, the smarter you look. So I'm going to draw you a sigma and a pi, and now your paper is going to look smart. So we're going to look at bonding. Let's review the molecule we started with when we talked about bonding, CH4 or methane. But instead of drawing it flat, I'm going to give it some perspective. I'll put carbon in the middle, draw a hydrogen going up like this, remembering that this is a model for 2 electrons. The other hydrogen will come here. Now, to give it some perspective, I'm going to draw this triangle, which means that this carbon-hydrogen bond is coming out at me, out of the screen or out of the paper, and then these dots means that this carbon-hydrogen bond is going back. Because of what's called VSEPR, valence shell electron pair repulsion, in other words, these electrons want to be as far apart as possible, carbon takes on a tetrahedral shape. And tetrahedral means that this hydrogen-carbon bond is 109.5 degrees. That is how mathematically you can get carbon-hydrogen bonds as far apart as possible. Well, the problem is a bond is the overlap between 2 orbitals. Well, carbon has 4 different kinds of orbitals, 3 that look the same, and 1 that's a sphere. So we have an s orbital, and then we have 3 different p orbitals, 1 up and down, 1 side to side, and 1 front and back. The problem with these are not 109.5 degrees apart. These are 90 degrees apart. So Linus Pauling in the 30s decided to invoke what's called hybridization to explain why or how the orbitals form around carbon. So instead of 3 distinct atomic orbitals, he said we're going to mathematically mix them to make 4 sp3 orbitals. And so we'll have an orbital here, which will overlap with a hydrogen 1s, and an orbital here, which will overlap with this hydrogen 1s. And now we have a picture of bonding in methane that will explain how you can get 109.5 degrees from 4 different orbitals, one's a sphere, and 3 orthogonal p orbitals. So whenever you see a carbon with 4 different directions around it, there are 3 things you need to know. It's tetrahedral, it has a 109.5 angle measure, and it's sp3 hybridized. So if I look at this structure right here, all of these carbons are sp3 hybridized because all of them have 4 different directions. Even though we don't draw the H's here, the H's are there. Similarly, if I had an ether like this, oxygen has 2 bonds and 2 lone pairs. These lone pairs need a direction. So everything in this structure here is sp3 hybridized. All of them have 4 different directions to go. Now, if we draw C2H4 as a Lewis structure, we'll draw it like this, put the C's in the middle, and we're going to need a double bond, so it will have a double bond. It will be an alkene. Looks like this. Now, if we look, we don't have 4 different bonds. We have 4 different directions. We have 3 different directions. The angle measure here is 120 degrees. This is carbon is called trigonal planar or trigonal. And the hybridization of this carbon, because it only has 3 different directions, is sp2. Now I'm going to take this molecule, ethylene, and spin it 90 degrees. So I'll put the carbons right here in the plane of the paper, of course, and then I'll have the H is coming out at me, and the H is going back. So now, let's look at the picture of bonding for ethylene. So each one of these carbons has 3 different sp2 hybridized orbitals. One goes out like this and overlaps with the 1s from that hydrogen. One goes back, and there's an overlap. One goes this way, so there are 3 different sp2 orbitals here. And then we have sp2 here, sp2 here, sp2 here, and then we have an overlap. Now this looks sort of funny, but we need one more bond. If we think about it, there's still an orbital left. We have used, in this structure, we've used the side-to-side p orbital and the front-to-back p orbital, but we haven't used the up and down p orbital right here. The up and down p orbital is going to overlap with the up and down p orbital on the other carbon. Now when I draw it like this means that there are 2 electrons both above and below the carbon-carbon bond. So if you look at the picture of bonding in ethylene, we have one kind of bond directly between the carbons and another one that is both above and below at the same time. These kind of bonds have different names. The ones directly between the atoms are called sigma bonds or sigma bonds. It's a mathematical kind of symmetry. The ones above and below are called pi bonds, a different kind of symmetry. So when we look at ethylene like this, it looks like both bonds are the same, but they're not. A double bond is made up of 1 sigma plus 1 pi. Now, a double bond between 2 carbons is stronger than a single bond between 2 carbons, but a sigma bond, because it's directly between the carbons, is much stronger than the pi bond, because the pi bond is not directly between the carbons. So even though double bonds are stronger than single bonds, pi bonds themselves are much more reactive because the electrons are not directly between the 2 atoms. So let's look at an alkyne or a triple bond and see the picture of bonding in it. So we have C2H2. We'll draw it, make that a little 2, draw it like this, and the Lewis structure has a 180-degree angle between the hydrogen, carbon, and carbon. It's linear, and the carbon, any carbon that has 2 different directions to go, is sp hybridized. So both of these carbons are sp hybridized, which means it uses 1 s and 1 p to make the bonds, or make the orbitals to make the bonds. I'm going to draw our atomic orbitals. Here's our s, and here are the p orbitals. Remember, hybridized orbitals are formed, mathematically formed from these orbitals. If I look at the bonding, this carbon has used the s, it's lowest in energy, and it's used the side-to-side atomic p orbital, to form the sp hybridized orbital. When we look at the bonding, we have, let's draw the sigma bonds first. So here are the sigma bonds. Sigma bonds look like hot dogs. In other words, when you skewer a hot dog along the axis and spin it, that's called sigma symmetry. Now we're going to use this orbital to form the first pi bond. It's going to look a little clunky, but it's sort of cool. This means there are 2 electrons spread out above and below our sigma framework here. And we're going to use this orbital, which is coming out of the page at you. So I'm going to try to make it have some perspective. And then this is going back. So the electrons are behind this blue pi bond. So the total picture of bonding in our triple bond is that you have 1 sigma and 2 pi bonds. And you really have a cylinder of electrons around this ethylene or acetylene molecule. So if we look at sigma and pi symmetry, sigma symmetry is if you take your marshmallow or your hot dog and you skewer it top and bottom and spin it. This is sigma symmetry. Now, if you take your marshmallow and instead of skewering it that way, we have it skewered top to bottom, that's pi symmetry. It's just a mathematical kind of symmetry, but the most important thing you need to learn from this lesson is that a double or a triple bond, when I draw all these 3 bonds in a structure, they're not equivalent, and that pi bonds are weaker than sigma bonds and therefore are more reactive.